of the day. But thank you for having me. It's nice to be here. It's going to be a bit of a strange talk, I think. I want to talk a bit about the science that we've done in the last 10 years of Galaxy Zoom. And then I want to talk a bit about why I think this sort of citizen science, the involvement of very large numbers of people in our data analysis, has a future into the next 10 years or so. And I'll finish by giving you some sense of what we're doing specifically in the context of LSST, but which I think has implications for all sorts of future projects and surveys. It will sound, I hope, like we knew what we were doing as I talk about the last 10 years. We didn't. We've been making most of this up as we went along. Because what happened was that this project existed by accident. I moved to Oxford as a postdoc in 2006. I was an astrochemist. I spent most of my PhD using the JCMT and running large Fortran models to look at chemical networks. And I got interested in star formation in the context of the environment of galaxies. So whether the chemistry of star formation changed if you took the same star forming region and put it near an AGN or in an elliptical instead of a spiral galaxy. And so my first test when I got to Oxford was to find a set of galaxies to study. And I'd been happily using the usual proxies for morphology that people had been using the first 10 years of Sloan. You know, color is basically the same. Most red galaxies are elliptical, so we'll just take the red ones and assume they're elliptical. But there was a student there called Kevin Schwinski who had just finished looking at 50,000 galaxies by eye to divide the ellipticals, the early types from spirals. And as a result, Kevin was deeply insistent that you had to put a huge amount of effort in to doing this. If he spent all of his time looking at 50,000 galaxies, then the rest of us should do this as well. Unfortunately, Kevin had also proved that he was better than a computer. That not only did he get a cleaner sample of galaxies sorted by morphology than you do by using proxies, he'd also shown he was better than any of the neural networks that people were deploying at the time. And so it really mattered, but he was very reluctant to look at another 950,000 galaxies and get through the rest of the Sloan main galaxy sample. And so without really thinking about it, we got some friends to knock up a website. This is what it looked like. This is what the web looked like in 2007. Nice frames written as a standalone application. And we thought we'd ask the public to answer the sort of simplest, useful question. So this is a randomly selected image from Sloan. Then we asked whether it was a spiral or an elliptical, a button for a merger, a button for the odd star that snuck into the sample. We also asked about the direction of the spiral arms, which I can tell you about some other time. And that was it, really. And the idea was that I would talk to local astronomical societies, to groups of amateur astronomers. And we gave 1 or 2 talks a month for 5 years. And roughly 50 people went home and classified roughly 50 galaxies each. In 5 years, we thought all of the galaxies would have been seen. This would be a nice side project, a nice thing, a piece of outreach as well as some science. But it's very hard to succeed slowly on the internet, as it turns out. And on the first morning, we were receiving 70,000 classifications an hour, which is more than one Kevin week, which is the unit of galaxy classification. And better than that, the results were pretty good. In fact, taken collectively, because we had enough people, we could have lots of people look at each galaxy. So collectively, the public were better, not only than the neural nets that were around at the time, but they were better than Kevin, who, bless him, made some mistakes, as you would if you look at 50,000 galaxies in a couple of weeks. But also, we realized we have more information. So you get, as you have lots of people look at each image, you get not just a classification, but you get some idea of confidence. So I can distinguish, a galaxy where 10 out of 10 people say it's a spiral from one where 7 out of 10 people say it's a spiral. So you actually get more information than you would do if you had a single expert go through. And so this has proved to be a very useful thing. Galaxy has evolved, it's been rebuilt many times. We immediately went from simple classifications to going back and asking people to classify the galaxies in as many ways as possible. How many spiral arms? Is there a bulge? Is there a bar? All of these extra things. We then got ambitious and we went and did the Hubble surveys to take us out to about a redshift of 1. GOODS, GEMS, COSMOS, CANDLES are now all classified and that data is public. People are using it. We're currently doing UKIDS. We've actually got UKIDS. We're doing the data reduction now. Doing the Southern Sky with decals. We're doing Gamma. So that's deeper images of mostly the Sloan galaxies. And we've even got to the point where the simulators are asking us to put galaxies into Galaxy Zoo. So one of the sets that we have live on the site at the minute is Illustris, which is one of the big cosmological simulations. And this came about because I'd heard too many talks from Illustris people who kept starting their talks by showing simulated images of galaxies, saying no one can tell the difference between this. And it turns out people can. I won't go on about simulations much, but this is a comparison of vote fractions. So this is the sort of weighted vote by which people say something smooth, which is a Galaxy Zoo sort of early type. And for high mass galaxies, this is greater than 10 to the 11 solar masses. Green is Galaxy Zoo. Blue is what the simulation thinks the galaxy is. You get pretty good agreement between the populations. But for lower masses, things are completely skewed. And you don't, sorry, I mean they're different. And so if you're below 10 to the 11, the simulated galaxies don't look like real galaxies. And that's good. Either that tells you something about how they're generating the images, or it tells you something about the physics in the simulation. And we're having an excellent discussion or argument with them at the minute about which of those two things it is. So I could happily talk for many hours about the many results that we've got out of Galaxy Zoo. Let me give you a flavor of some recent stuff. One of the things that we keep coming back to in terms of detailed morphology is the presence or absence of bars in disk galaxies. So this is a plot from Brooke Simmons' work. There's lots of Galaxy Zoo stuff here. So this is the bar fraction. This is the fraction of disk galaxies that have a bar measured over a large redshift range. So this is the Hubble data as well as Sloan. The pink triangles and the black dots here, as well as this blue cross, they're all Galaxy Zoo results. And you see you get this nice result, whereas you go back to higher redshift, you get back to a redshift of 1, the bar fraction drops dramatically. So something's changed in the disk population over the course of this relatively narrow redshift range. We think this is linked to the idea that you need a stable disk in order to support a bar. But we almost get the most interesting result of all. So if you go all the way back to redshift 1.5, we find a few barred galaxies. And so that confirms the general trend. And in grey here is a theoretical plot of what this decline should look like. But the fact we find it few makes those galaxies targets for interesting follow-up. Why is it that those galaxies have managed to form bars early on? We've also looked at the properties of bars locally. This is a plot from my PhD student, Shandor Crook, who's just submitted a paper with a huge set of barred galaxies. And I want to show you this just to give you an idea of that sort of sense of confidence that I was talking about. So these are selected at different p-bars. So this is the Galaxy Zoo vote fraction. It's the weighted fraction of volunteers who say there's a bar in each of these images. So this one's pretty obvious. Everyone who saw this galaxy said it was barred. And then you can see it drops down to these things where those are probably real, I think, but where only half of the weighted vote, of people said that there were bars there. So even at these low vote fractions, there's useful information. Anyway, Shandor did a good job of assessing which of these are real, of putting a threshold on, and so we can look at the properties of the bar population. So this is color magnitude diagram. So normally you have the red sequence of galaxies, mostly, but not all ellipticals up here, and blue cloud down here. And this is the excess of barred galaxies. So you see that this is an old result. It's nice to see confirmed that mostly it's the redder galaxies that host bars, or at least if you're a red galaxy, you're much more likely to host a bar than if you're a blue one. Shandor's also done fits to the whole population, so he's split up using a variation of Gelfit M, and he's split out the galaxies so that you can divide the disk from the bar from the bulge. You look at the colors and the properties of those separately, and so this is split by mass, but particularly at low mass, you see the bulge is redder than the bar, which is redder than the disk on average. And so this has interesting things to say, I think. The idea here is that the bar may be responsible for transferring material from the disk to the bulge. And this is the sequence that you'd expect if that's exactly what's going on. So you have a nice blue disk, material travels along the bar, gets quenched, so you have a redder bar, and then it ends up, the older population ends up in the bulge. However, even in doing, this is a big job. It's taken most of a couple of years to deal with a very large set of galaxies. But even when you're dealing with large data sets, it's worth actually paying attention to what you're looking at. And one of the nice side things that came out of this was that Shandor noticed there's a set of galaxies where the bar is offset from the center of the galaxy. Having noticed that, we had to go back and do the fitting again, well, by which I mean he had to go back and do the fitting again. We previously forced the bar and the disk to have the same center. But if you don't do that, you find that there's a set of galaxies with offset bars. They're not very offset, maybe a kiloparsec or two. And these are some examples. And they're an interesting set of galaxies. They're small. Of course, there's a famous example of an offset bar. If you think about the LMC, which has a very definite bar, which is very definitely not at the center. And most of these are about LMC size. Here's the mass distribution. Yellow is a comparison sample, and blue are these offset bars. So there are a few massive ones, but they're almost all less than 10 to the 10 in stellar masses. You can ask yourself, why is the bar offset? And the general theory for these things, there's a nice paper by Pardee et al. That describes this, is that this is a galaxy that's been disrupted by a flyby. So it's not a merger, but you have another galaxy fly by, disrupts the material, and the disk sloshes about in the gravitational potential. And actually the bar stays static. And so you can predict, if you simulate this is the Pardee paper, you get this really nice prediction where you essentially have a damped oscillation around the center. And so you can use this, you can say something about the fact, if you believe this model, the greater the offset, the more recent the interaction must have been. You obviously need to calibrate that, but across the population, that's true. And so this is quite a nice set of simulations. We've got a set of a few hundred galaxies to test this with. And so we went back to the Sloan data and we went looking for companions. We want to see the interloper and see if we can catch them in the act. Unfortunately, with the Sloan data, we don't have spectra, so we're making guesses about which galaxies might be companions. And so what we did was compare to a nearby sample. And this is the result. So I'm not going to bother going through the guess. This is all the possible companions of our different sets of galaxies. And we don't see an excess of companions for these nearby galaxies, for these offset galaxies, compared to a random selection of similar galaxies with similar mass. So either these images aren't deep enough to show us the companions, we need to do an observational follow-up and actually go and check that this result is true, or something else is causing these bars to be offset. And one of the suggestions is that it might be actually an effect of a lopsided dark matter halo. So if large-scale structure has affected the halo, or these galaxies have just assembled, then you'd see the baryons displaced in this way. So it's an exciting sample of galaxies, but this whole line of research just came out of just looking and noticing that there was something interesting there. And that keeps happening in Galaxy Zoo. As another example, people for a long while have looked at bulgeless galaxies. So this is NGC 4395. This is a nearby flocculent spiral. Sort of got more well-defined arms than an irregular, but it's sort of a lake-type spiral. And there's no bulge at all visible in this image. If you do the dynamics, there's no bulge there either. And it was studied more than 10 years ago and found to have a black hole that's only 300,000 solar masses at its center. It's a factor of about 10 less than you'd predict from the standard black hole relation, black hole to stellar mass relation. So why do I care? Why am I telling you about bulgeless galaxies? The idea is that galaxies like this are guaranteed merger-free, right? So the simulations tell us that any significant merger, maybe even a merger as small as a 10-to-1 merger in mass ratio, kicks stuff out of the disk and ends up forming a significant bulge, which could be seen. So when you look at a galaxy like this, you're seeing one that hasn't been affected by mergers. And so it's a laboratory for understanding the effect of mergers on the galaxy population. Mergers have often been used to explain the Megorian relation, black holes mass to stellar mass relation. And so the fact that this has a small black hole and no merger history seems to confirm that picture. But it's one galaxy. And so from Galaxy Zoo, we can go from one to many. So we start with 1 million galaxies roughly in the Sloan main galaxy sample. We end up, in our most recent work, studying 101 galaxies. I think it's one of the things that's interesting about modern survey astronomy is we collect this very large sample, and then by the time you control for everything you're interested in, you end up studying 100 galaxies. I think that's a pattern that's unusual to our field and something we all keep doing. And when we talk about big data, we should worry about that. So why have I got these 101? These are all Bulge Mass, as selected by Galaxy Zoo volunteers and then confirmed by us. And from where you're sitting there, they look like they have central bulges. Those are all AGN. So these are bulgeless galaxies with growing black holes. And so if we believe the simulators, and these are merger-free, these are AGN growing under purely secular processes. What we did was we went and used the Sloan spectra, supplemented by work from INT. And we went and measured the black hole masses for all of these galaxies, and then we put a constraint on the bulge mass. So we said, if there's a bulge there, what's the maximum amount of light from each galaxy that we can attribute to a bulge? And here's the result. This is the bulge mass versus the black hole mass. In red, it's an old sample of bulge-dominated galaxies from Herring and Rix. So this is sort of the standard relation that one would expect. And in black are our points. Some of them are measurements. Most of them, we only have limits on the bulge mass. So we're trying to be conservative here. And then you can either take the convincing or the statistically correct result. So let me give you both. So this black line here is what happens if you take all these limits as points and then you do a best fit to them. And you can see it's distinctly different from the red line. Or if you do the right thing and consider these limits as samples from an underlying population, and you do a Bayesian estimate of what the underlying population is, this is the best fit line, which looks utterly unconvincing. It is actually the right way of doing things, so we show both. Thank you to whoever the referee was. Anyway, the point is that these are different, and this is, I think, very exciting and also utterly boring at once. Because what I've done was I've selected a set of galaxies which have little or no bulges, and then shown that their bulge mass is lower than you would expect for given black hole mass. So that's not really the exciting bit. The exciting bit is when I do this, because this is not now, this is still the black hole mass, but this is now the total stellar mass of the galaxy. And when you look at the total stellar mass, not the bulge mass, they look like normal galaxies. And so in other words, if you consider total mass, not bulge mass, these things have assembled the right size, right mass rather, black holes through purely secular processes. All the simulators are wrong, and we can talk about that later. We're in the middle of doing a proper check of that, and it seems right. So in other words, mergers don't play a significant role in growing most black holes. And if you're a galaxy person, this adds to, there's a sort of growing sense, I think, that major mergers at least look great, but don't have much to do with what's going on in the long-term history of the galaxy. Most stars, for example, don't form in merger-triggered star formation. Black holes, we show here, don't grow primarily through merger processes. And I could, and would happily, talk to anyone about the rest of the stuff we've been doing with Galaxy Zoo. Let me broaden it out a bit, because the other thing that happened when we started publishing papers using Galaxy Zoo results, people kept asking us for the data, so we've done a good job of sharing the Galaxy Zoo data. There are big catalogues available. But the other thing that happened was that people started calling us and asking whether the people who we collaborate with to look at galaxies, our volunteers, whether they would be suitably distracted by other data sets. Because it turns out it's not just us that have this problem of data that was amenable to being viewed, to being looked at, and from where people were completely overwhelmed by the size of the data set. So, for example, here is a typical image from a data set from my friend Tom, who's he describes himself as a penguinologist. And so Tom used to go to Antarctica once a year, visit the same places on the Antarctic Peninsula, the bit that sticks up towards Argentina, and count penguins. And then he'd come back, and and his research was essentially slowly growing time series that showed the health of the colony as judged by the number of penguins in the place when he happened to get there over the course of many years. And he's looking at the effect of climate change, of tourism, of scientific research, of fishing on these penguin colonies. Then he discovered that you could buy cheap cameras. They're actually designed for lazy hunters. The idea, the marketing for these things is that you go and put them in your woods, and then you know whether it's worth going to kill the deer that are there or whatever else. But they're about $200 each, and they survive when wired to a car battery, an Antarctic winter. And they take a picture every hour. So Tom still has to go to Antarctica every year. Like, he feels about that much as I do about missing my trips to Hawaii to come and use telescopes. You lot have made it more efficient. So it's important to Tom that he still has to go to Hawaii. But what he does go to Hawaii, go to Antarctica. Those places are different. There are no penguins here, right? Anyway, so he still has to go, but these days he has to go to change the batteries and collect the cards out of the cameras. Then he comes back to Oxford with something like 6 million images of penguins. And it's still only him and a PhD student. But his research comes down to how many penguins are in this image. So let's do some audience participation. Anyone want to venture a guess? 3, yeah. There's usually somebody in this sort of audience who says 2.4. It's just going to show you've got to pose the question correctly. Let's try another one. Just shout out when you... Oh, no. 0 penguins. Right, so we were supposed to be counting penguins. Ready? So you've all demonstrated a very human quality, which is not carrying out the instruction you were given when given wrong input, right? So one of the key things about people being asked to classify, if you're a neural net trained to count penguins on images like the first one, you'll give me an answer here. We tried this. The neural net tends to say that there are 3 big penguins in this. That's the wrong answer. Whereas in humans, all sorts of different reactions. Tom tells me that when he set this camera up, there were no penguins. So it illustrates the importance of coming back more than once. This is a more typical image. And so we realized that having built software for people to classify galaxies, it was easy to build software for people to count penguins. And so this is Penguin Watch. The original name was Penguin Hunters. You can sort of see there's a little bit of that left in you. But apparently that's not how you pitch a biology project. So Penguin Watch has become extremely popular, and Tom's penguins are now happily counted, and they've been able to do things like establish when and where and why the penguins come back early on particular years, as well as look at nesting behavior and so on. In fact, the number of people who want us to build projects for them has got so overwhelming that we've now resorted to building a tool for project building. And so if you go to zooniverse.org/lab, you can build your own Zooniverse project using a set of online tools. So if any of you have used WordPress to build a blog, it's sort of that sort of level of complexity. You don't need to know anything about web development. And this is working pretty well. The number of projects is increasing rapidly. We just launched our 100th a few weeks ago. We're now on 108, which is more scary. And each of those projects has a science team who are responsible for using the data and promising to the volunteers that they're going to do something useful with it. To give you a flavor, here's a not complete set of astronomical projects, as well as Galaxy Zoom. We've done with Meg, actually, Comet Hunters, which was looking at active asteroids, Solar Stormwatch, looking at CNEs. A Milky Way project went through Spitzer data to look at bubbles around star-forming regions. Andromeda project is a cluster counting project. It was hugely popular. Finding clusters in the FAT big survey, the Hubble big survey of Andromeda, was incredibly popular for reasons I don't understand. We're about to do M33 as well. Space Warps, that's Phil Marshall and co, looking for gravitational lenses. Planet Hunters, again, Meg was involved, and a couple of other exoplanet projects. We've done simulations of mergers. We've matched radio to infrared data. Planet 4, we've looked at the polar regions of Mars. There's a couple of asteroid hunting projects, some more solar stuff. Lots of supernova projects I'll talk about in the minute, and Disk Detective, which recently found a new brown dwarf 20 light years away. I've got the number right. So this has become a sort of standard set of ways for people to interact with data. Certainly when it's proposal time, we get a lot of phone calls from people going, can I promise that I'm going to do a Zooniverse project? My data, and the answer is yes, the service is free to use. And as long as you're actually going to do research with it, people are welcome to come along and use it. And this is a good thing, because we've also looked at the effect on the volunteers of participating in these projects. The first thing we did was ask them why they did this. which seemed like a good question to ask. And the exciting thing was that we weren't reaching the people that we thought we were going to get. Remember, I said I thought we were going to get amateur astronomers. And it turns out that's not the audience. Amateur astronomers already have astronomy in their lives. They all know about galaxies in the UK, and they often promote it for us, but that's not what they do. Instead, we get a bunch of people who are just inspired by the idea that they can help. So the number one reason for participating isn't love of astronomy or a desire to make a discovery, it's I want to help. And so that gave us the confidence to build these other projects. It wasn't anything magic about galaxies, it was this sense that we could offer people the chance to participate, to do something real and help us find out something about the universe. And then the other thing, and then we asked people how it had affected them, and people said, more than 80% of participants said they were more likely to seek out scientific content as a result. And that's exciting because these people aren't what you might categorize as science fans on the whole. So people in education research often split people into three categories. You have the science fans who, when they go to a new city, immediately go and seek out the planetarium or the science museum. They probably read Scientific American or read blogs that talk about the latest updates. And I think we often communicate to those people. Certainly, in Oxford, when we put on public lectures, that's who turns up. When I work for the BBC, my guess is that's in a large part, that's who our audience is. There's also the science phobic, who are much harder reach. But in between, there's this category of people that people call science attentive. And these are people who, if they're reading the newspaper and there's a science story, they will read it. If they're surfing the channels and they see something interesting that's got galaxies or penguins in it, they will stop and watch it. But they don't seek out scientific content. And that's who our audience is. And yet they're telling us that because they've participated, they're much more likely to go and find out things. But this is pretty terrible social science, right? If we knew what we were doing, we wouldn't be asking people, we'd be looking for evidence that this is what's going on. So we started to do that. Here are some sets of images we've inserted into various Zooniverse projects, and we've asked people questions about them. The top row are not randomly selected images, they're carefully selected images, which is the opposite of random. And we just asked, what is this? As a way of measuring the baseline scientific knowledge of people who are participating. And so it's interesting, for this first one, you get everything from bacteria, which is wrong, to, some people say it's a thing in space. Some people say, it's a nebula. Some people say it's the Crab Nebula. Some people say it's M1. Some people say, that's the Hubble image of whatever, so you get some sense of what's going on. The same's true with the other images here as well. I won't embarrass you by going through the list. And then we ask specific questions about scientific topics that were to do with the subject in hand. So if you're on Galaxy Zoo, you've got questions about galaxies and about cosmology. If you're on Snapshots, you've got questions about wildlife and conservation and so on. And what we showed was that the more involved in a project you are, the more you know about the scientific topic that you're engaging with, even when we control for the amount of general scientific knowledge you come in with. So that's evidence that learning's actually happening, or rather we're inspiring people to go and learn. Because the knowledge that people are acquiring is not stuff that we teach them. Right? When you go to Galaxy Zoo, you don't start by reading a tutorial that explains the basics of galaxy vision. It just says, we want you to classify the shapes of galaxies, but people were inspired to go and find out more. So these things are acting as engines of motivation. They're inspiring people to go and learn. And when we combine that with a survey, we found there's no relation between the likelihood that you're going to learn stuff and your age or your gender or your level of education. So we have a broad audience who are being converted to go and learn stuff, which is really exciting from an outreach point of view. And so therefore, I think it's really important that we get to keep doing this. And that's problematic because most people's vision of the astronomical future looks a bit like this. We all know that the robots are coming in sort of two senses. There's more and more data coming our way. And so the idea that we're going to have people look at it is slightly ridiculous. But also, you don't need convincing, I suspect, that machine learning has made huge strides in the last few years. Facebook now recognizes your friends when you upload photos. Google can tell you where in the world a particular image is. and so on. And so even voice recognition has gone from being a joke a few years ago to being something that people use. And so it seems ridiculous to say that we're special, that our astronomical problems will be resistant to being solved by machine learning. And there are people in institutions all over the place whose PhDs and postdocs are predicated on building the definitive machine learning solution to whichever of these problems is there. And because if there's magic here in the project, it's that people are doing something real, that means that citizen science will die out in the near future. So let me argue my way out of that box and try and convince you that that's not true. And I just want to do that by splitting into, there are two sets of things that happen in citizen science. There's classification and then there's discovery. So classification is mostly what I've been talking about. There's also finding weird stuff, like the VUlva, which I'll talk about if I've got a second. So for classification, it's easy to see how machines might help us. So for example, here are, I'm going to just start putting images of animals in to try and keep you interested as well. These are images from Snapshots Serengeti. These are motion-sensitive cameras in the Serengeti National Park. In this case, the task is to classify the animal. Giraffe, lion, stripy horse. And you can see there's some excellent, some obvious stuff you can do with machine learning. Even if you don't know what these things are, you could say all of these animals are of the same type. And so you can then use that as an accelerator on your use. And Alex Hocking from Hertfordshire has done this with the Sloan survey. We're completely blind. He used an algorithm to sort Sloan into 100 different categories of galaxies, and then you just have to go through and label a few in each category. So it can definitely help the classification. But there's a problem, which I'm trying to convince people to call the Zorilla problem. So for these animals, I've added a porcupine. These are all pretty common. And eventually you can build up big enough training sets that machine learning can solve this problem. We've published papers using the Snapshots Serengeti data set that show that we can now, we've got an excellent giraffe recognizer, for example. Some are harder than others, but once you build up enough training set images, the modern machinery of machine learning kicks in. Because that's what's powered this improvement. It's the availability of very large labeled data sets. Facebook can recognize your friends because for 10 years we've all been happily labeling our friends on Facebook. Google can recognize places because we've been searching for images of places. And our Snapshots Serengeti system can recognize giraffes because we gave it 100,000 labeled giraffe images. But when you look at rarer things, that doesn't work. So this is a Zorilla. It's a bit like a skunk. Anyone heard of a Zorilla before now? There's one kid's book that does, it's A is for alligator, B is for Zorilla. And so occasionally in an audience, I find people who've got that book who are relieved to discover that it actually exists. So Zorillas show up in 1 in 3 million images in Snapshots Serengeti. And that's a real result. That's not a guess, that's a measured number. And so, no matter how long we operate this camera network for, we're never going to build up enough training data to build a Zorilla recognizer. And astronomy is full of Zorillas. This is my space Zorilla. If you think whether you're looking for gravitational lenses or whether you're looking for unusual supernovae or whatever, we don't have big data in this sense. The things we're interested in, remember, tend to exist in the hundreds and thousands in our large surveys. The number of strong gravitational lenses found today is what, a couple of hundred maybe? You know, with LSST we might get 2,000 or something, or 20,000 if you're optimistic, but that's not large training sets by the standards of modern machine learning. And so there are these places within the science that we want to do where brute force machine learning is not going to solve it, at least not in the next 10 years. And so we have to think about how to handle this differently. So here's an example. This is work led by Darrell Wright, who's now a postdoc in Minnesota, was with us in Oxford and in Belfast before that. He's taking the Pan-STARRS data and he's looking for supernovae. He was given this task as a PhD student. Every Monday he came in and he reviewed the data, and then he went and taught himself machine learning, and then he built a trained neural net based on expert classifications that does a reasonable job, but not a perfect one of classifying these supernovae. When he came to work with us, he created this project, Supernova Hunters, which at 3 p.m. UK time every Tuesday releases a week's worth of data. And so this is the traffic to the site. So we sent a newsletter, said there's new supernova data available, people rushed to the site, did that the week after and the week after, then we stopped sending a newsletter. But now we've got a trained set of volunteers who know to come to the website at 3 p.m. every Tuesday. Actually, they come at 2:58. We see the spike in traffic just beats. And these days, within about an hour, they classified a week's worth of data. And so then for this, and then what we do is we run Darrell's machine learning against the same data set. So this is the data set classified by machine and by human. We throw out the stuff the machine says is definitely not a supernova. This is most of the stuff with no change at all, we just throw out. So every dot here is a candidate. Green are things that the experts say are not supernovae. Yellow and red are possible supernovae. Blue are asteroids, which in the scheme that we've got should be classified as supernovae. You get rid of them later, right? You discover they're moving. And you can just see from this plot, I'm really proud of this work, that there's no threshold. Normally what you do is you take the machine score and you put a threshold. You say, okay, this is my candidate set. Or you take the human score and you put a threshold and say, okay, this is my candidate set. And you can see that there's no horizontal line I can draw, or vertical line, that beats a diagonal in terms of splitting the rubbish from the rest. So in other words, a combination of, this is real data with a real project, with real people and real machine learning, and the combination of human and machine outperforms either. And you can see why that is if you look at the different results. On the left is the machine, on the right is human. And you can see the machines give you this nice smooth classification, does all right, but isn't complete. Whereas the humans, we deliberately run this project with very few people looking at each piece of data on the grounds that we want to simulate a world in which we're completely overwhelmed with the amount of data, so we have to make quick decisions. You can see there's much spikier and much more scattered. What's happening is the unusual stuff gets promoted up by people. So the supernovae in bright galaxies, the supernovae with a star in the distance, the ones that are at the extremes of the parameter set, get classified well by the people. And so when we combine the two, it's what we get. So this is completeness versus purity. You want to be in the top right of this curve. Red is human, yellow is machine, and then blue is combined. And so this works very well, and we can do this. Meg, how long do I have left?
You've got about 15, 20 minutes.
Oh, cool, good. So we can actually do even better than this. So using a technique stolen from the Spacewalks team. The Spacewalks was our gravitational lens hunt. We used data from CFHT, and their big lens search. There are other data sets in there now. The nice thing about gravitational lenses is they're easy to fake, or at least they're easy to simulate, which is a much better word. And so we put into this data set a bunch of simulated lenses. That's good because we can give feedback to people. The biggest problem we have is that people want to be reassured that they're doing this correctly. And so simulated images are great. We also had some guaranteed lens-free images that we'd inspected, so we could give people feedback that way. But we could also measure the performance of different people based on how they do on our data set. And so you get graphs like this. So this is the probability that somebody says there's a lens if there's a lens versus the probability that there isn't a lens. They say there isn't a lens when there isn't one. And each dot here, this is 50 randomly selected people. And so most people are pretty good. They're up here in what the Spacewalks team call the astute region of the parameter space. Some people down here are obtuse. They're wrong a lot of the time. But notice that if you know that somebody is wrong all the time, they're exactly as useful as somebody who's right all the time. This works in life as well. Many of you may use the strategy in your everyday lives. And so we get more information once we've measured this, and you can actually improve things. But also, we can start playing with tactics. So for example, anyone on the right-hand side of this graph is an optimist. They tend to think that they're a lens there, and everyone on the left is a pessimist. So you might do things like, if I've got weak evidence that there's a lens in this image, so maybe 2 people have looked at it and they say there's a lens there, I might show it deliberately to a pessimist. And if they say there's something there, my confidence goes sky high. Equally, if I'm about to get rid of an image, I should probably show it to an optimist. And we've done work with Mel Beck at Minnesota and others who have worked on using this sort of information for task assignment. And if you could, instead of handing stuff out randomly, but pass the image to the right person, you can get a factor of 10 improvement in efficiency. That's not what we're going to do here. We're just going to use it for accuracy. And same graph as before, things get even better. So the like this blue line here is just machines, just people. Sorry, this light blue line is just people that are paying attention to who's any good, and then the dark blue line is everyone. So we're doing pretty well with this combination, and this is an obscure slide designed to make you believe that we built all of this into the system. So you can now, if you build a project using our project builder, you can now run this sort of analysis yourself on your own data with your own machine learning, and combine human and machine classification as a matter of course. And so the future isn't the scary dystopian robot, it's more like this. And that's the Zorilla game, this. There we go. Friendly machine-human interaction. Except that there's a problem with what we want to do is discovery as well. And one of the great things, the most fun we've had in the last 10 years, has been following up on random discoveries. So this is the VUlva, which is discovered by Hanny van Arkel, who's a Dutch school teacher. Notice there's this blob. It turns out this is hot gas. First spectrum of it told us that it was 50,000 Kelvin, but with no stars, there's no continuum. Mm-hmm. And so something has ionized this, and we thought, okay, well, this is a slightly disrupted galaxy. This is actually a LERG, so it's very luminous in the infrared. You can see in the morphology it's been studied. This is clearly an AGN. You can work out it's actually has to be nearly quasar strength, but if it's that active, then you can have a jet coming out. Most jets in active spiral galaxies come perpendicular to the disk. You can see why this would be ionized. It's very exciting. But we looked at it with XMM and discovered it was completely inactive. And so what we think has happened is that the VUlva is telling us about the state of the AGN 50,000 years ago because of this projected distance. It's an echo. And so this would have been 50,000 years ago, would have appeared as a very bright active AGN. In fact, it would have been visible in binoculars. The nucleus would have been about 8th magnitude. But it's faded rapidly over a very short timescale. So this is very exciting. Hanny became a bit of a celebrity. She was on the news in Holland. We flew her to a AAS meeting to meet astronomers, which was very exciting for the astronomers. People kept coming up to her. Eminent people kept coming up to her and going, "Are you the Hanny van Arkel?" just wonderful. But it meant that other Galaxy Zoo volunteers wanted to find these things too. So we now have a whole set of Vorwerkis, which is the diminutive version. They're mostly smaller. These are all gas clouds. These are all HST narrowband imaging of gas clouds, which show signs of being ionized by AGN. And at different distances, you can read off the ionization history. And so for this sample of AGN, we now have this nice set of ionization curves, which are very noisy, but for about a third of the galaxies that we've looked at, show this very rapid decline in ionization. So we're being able to probe AGN on timescales of thousands of years. And that keeps happening in Galaxy Zoo and other projects. We found the green peas. These are small, round green galaxies. They're called peas by the volunteers for obvious reasons. The group of volunteers involved called themselves the Peas Corps, which it took me ages to realize was a joke. These turn out to be the highest specific star formation rate galaxies in the local universe. So they have the kind of star formation per unit mass you expect of Lyman break galaxies at a redshift of 3, but locally and in very underdense environments. So they're being used to study sort of ionization breakout and to understand what similar galaxies at higher redshifts would have been like. The nice thing about the peas is that once you know they're interesting, you can find them automatically. So this is a set of color cuts that more or less give you the peas. And you can find them in papers going back to the 50s in catalogues of emission line bright galaxies, but it needed a group of people to say, hang on, there's something distinctive about this group of systems. And it's not just Galaxy Zoo. There's the light curve of a particular star in Kepler, been studied by planet hunters. You see a couple of small dips here that people thought were planets, and then our volunteers pointed out that something odd was going on. This is a 20% dip that lasted for a day or two. And then towards the end of the Kepler K1 mission, it went slightly nuts. The volunteers called this the WTF star, which we managed to get into the journal. In monthly notices, you have to spell out acronyms. So this is Where's the Flux? Definitely what it stands for. And this is better known as Tabby star or Virgin star. But lots of people on this paper are citizen scientists. And if you look at what happened before any of us got involved, here's a dip. This is the discussion forum on the Planet of the site. Somebody saying there's something interesting going on. I like definitely SETI should look at it as soon as possible. But these comments lead on to a group of people, particularly somebody whose username is Nighthawk Black, who's the second author on the paper, who went and got the rest of the Kepler data, pulled it down, compared the transits, said, look, the eclipse profile looks the same, can't reconcile the smaller dips, and he ends up making his own model of the system. And so this is his suggestion, where he's going, okay, well, what might be happening here is we've got a planet with a disk going in front of the star, which causes the profile that we see. I also like, he notes, the true situation is probably nothing like this, but it seemed like a good opportunity to rampantly speculate in paint. More people's papers would benefit from that sort of thing. But the point is that for this to happen, and this star is still the object of study, it's actually, thank God, dipping again right now, which means that we have a network of people doing spectroscopy, and here's the last 3 months worth. So it's only got a new series of dips and we can do spectroscopy and so on. My nightmare was that this would never dip again, that we'd never know what it was. But for this thing to be found, we needed volunteers to be reviewing a large amount of data and enough volunteers that somebody said there's something unusual here. And then we needed a set of advanced volunteers who'd sorted themselves into a community, people like Darren, to come along and collaborate on understanding whether that was really interesting or not. And then we needed lines of communication between them and professional astronomers who could help. So we went, for example, and looked at the infrared data and showed that the disk model doesn't work. There's not enough infrared flux, which has led to all sorts of speculation about what this might be. And so that's what we need to build for the next generation of surveys. And what I want to get across is that's in conflict with all the nice chat about efficiency that I had when I was talking about classification. Because if I'm handing over a large part of the data to machines, if I'm being careful about who should see what, then I worry that we lose this ability to make the unexpected and serendipitous discoveries. What's interesting is we think like computer scientists, and there's a whole bunch of computer science about how to assign tasks to imperfect classifiers, and we forget that our classifiers are volunteers and that they have the capacity to do this. And we can show that there's that conflict in very simple ways. These are images from Snapshots Serengeti. Most Snapshots Serengeti images don't look like the ones on the right, they look like this. 70% of them don't have any animals in. The cameras are either malfunction, in which case they fill up their card by triggering repeatedly, or sometimes the grass gets warm and waves, and if they're infrared or motion triggered, we get a lot of pictures of the grass. At night, sometimes it's just being triggered by an animal that's too far away to see. And so we thought, fine, it's easy to write a machine learning classifier that gets rid of the blank images. So we did. We thought people would be happy and they get to see more images, but they did much less work and enjoyed it much less. Because blank, 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 zebra is much more interesting than zebra, 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 wildebeest. And so even on this very trivial level, we need to understand what it is that our volunteers want. We need to understand what it is that's causing the learning that I talked about. And we need to understand what it is that might make them triggered to do these serendipitous discoveries. So that's what we're trying to build. So we've got a system that allows people to build projects quickly. We've got a system that allows you to combine machine learning and do task assignment. But as we worry about LSST being built, and every time I go to their website and look and see that construction is now real and this stuff is happening, what I'm worried about is how we better understand the more complex behavior that's led to all the interesting stuff. Because I worry that otherwise we're designing a system that can only discover the stuff we already know about. That's the challenge. I hope some of that was interesting. I'm happy to talk to anybody who's got projects or ideas or thoughts about what we should be doing. Thank you very much.